Go to the second part of linear motion. So we are going to be looking at the graphs of linear motion. First is the distance time graph. Here, this is the distance time graph. Distance on the vertical axis, and let me change this markers. Distance on the vertical axis and time on the horizontal axis. This is what's called a distance time graph. It shows, the distance traveled by an object over a particular period of time. In this graph, it is shown that the the reckoning of the object distance starts from a particular value. Let's say from 2 meters to, let's say, 10 meters. So if you want to find, let's say this time is 5 seconds. If you want to find the speed now, the speed is changing distance, which will be 10 minus 2 over time taken, 5 seconds per unit time. Changing distance per unit time is speed. So you'll be doing 10 minus 2, 8 meters over 5 seconds to get your distance per unit time, or speed. So that's how the distance time graph looks like. The slope under the distance time graph, gives the slope of the distance time graph gives the speed of the body or object. Speed is equal to slope on the graph. Speed is equal to slope on the graph, and the slope is change in distance over change in time. Take note of that. Speed is in meters per second. Next is the velocity time graph. Velocity time graph is more common than distance time graph. Now, there are many different types of velocity time graph depending on the nature of the motion of an object. For example, if a question says an object travels at a speed of 15 meters per second. At a speed of 15 meters per second, this is the only thing I can mark. This is the only thing I'll be able to mark. Object traveling at a speed of 15 meters per second. I will only be able to mark this. This is all I'll be able to show on my graph. You understand? I will stop there. But if the question says an object travels at a speed of 15 meters per second for 10 seconds, then I can do this. It travels at this constant speed for how many seconds? 10 seconds. So that would be my distance time graph. Although this part is not part of the graph, just an indication of how long the car traveled. You understand? At 15 meters per second. So this is my graph. Let me draw another example. It can also occur that, let me number it. Let this be our first example. Let me use a letter A. Let me give you another example of a velocity time graph B. Let's say velocity meters per second, time in seconds. Let's say we have a situation where a car starts from rest. This will be rest, 0 meters per second, and accelerates uniformly to a speed of 20 meters per second in 5 seconds. So this is what my graph would look like. I hope you can see that. A car starts from rest, accelerates means its velocity is not constant like this or like this. Do you understand? The velocity changed. Accelerates means the velocity increased with time. For what? For 5 seconds. From 0 meters per second to 20 meters per second. So this is how my graph would have looked for that kind of motion. Let me draw another one. Just so you can be very familiar with what goes on in your examiner's mind every time they give you a question in motion. Velocity in meters per second, then time in seconds. Now, let's say in this case, our question says a train moving at 20 meters per second. I'll mark this. If a train is moving at 20 meters per second, this is all I can mark on my graph. A train moves at 20 meters per second. And then maybe a train moving at 20 meters per second accelerates uniformly to a speed of 50 meters per second. So it has increased in velocity. Can you see? To a speed of what? 50 meters per second. So that's how the illustration of my graph will be. Now, another information I'll need to put, if I have it, is the time. Let's say the question indicates that a train moving at 20 meters per second accelerates uniformly to a speed of 50 meters per second in how many seconds? You ask yourself. How many seconds? Let's say the question says in 10 seconds. This will be my velocity time graph for that motion. You can see in this case, the train did not start. Our question did not tell us that the train started motion from 0. It might have started from 0 in some other, you understand, at some other time. But during the reckoning, the initial velocity was 20, and that velocity increased. Maybe the car accelerated and the velocity increased from 20 to 50 meters per second in 10 seconds. That way, my graph will show the velocity changing from 20 to 50 in what? 10 seconds. This will be my velocity time graph for that illustration. There are many, many different kinds of velocity time graph. These ones are showing acceleration. Let me give you one that shows deceleration. Velocity in meters per second. Time in seconds. So, for example, let's say in a question, a car moving at 40 meters per second. I can only mark that because the time is not stated. A car moving at 40 meters per second, had its brakes applied and slowed down. That means it decelerated to a velocity of 10 meters per second. In how many seconds? You might want to ask. Let's say in 8 seconds. This will be the graph for that motion. You understand? This will be my graph for that. So it shows, my graph now shows the initial velocity. Shows the initial velocity. This is my U. Shows the final. This is my V. And shows the time. So that's how the velocity time graph of that kind of motion. This is how the velocity time graph of that kind of motion will be drawn. A train or a car moving at 40 meters per second initially had its brakes applied and slowed down or decelerated to 10 meters per second in 8 seconds. So that's how my graph will look like. Let me give you another one. Here, let's say E, velocity in meters per second, time in seconds. If for example, I say, or we are told that a train moving at 200 meters per second decelerated to rest. Rest means 0 meters per second. Rest means velocity is 0 meters per second. Or decelerated to stop. For rest, we use rest or stop. or halt or stoppage, it all means that the velocity is what? 0 meters per second. That rest can sometimes be, final or the initial velocity. Just know that rest means a point in motion where the velocity is 0 meters per second. So this is how my graph would look. If a train or car initially speeding at 200 meters per second, decelerated, maybe slowed down, maybe due to application of brakes, to rest. If it slows down from 200 meters per second to rest, this is how my velocity time graph will look. If the time is indicated, let's say that slowing down or that deceleration happened in 20 seconds, my 20 will be written here. Can you see that? So this time from 0 to this point is 20. So those are just the basics of velocity time graph. Let me draw some some more examples for you. Let me draw some more examples for you. Sometimes we have 2 or more stages. All of these motions I've drawn here, all of these velocity time graphs I've drawn here, just have, one stage in them, one stage of motion. Sometimes a car can start from rest where velocity is 0 meters per second, accelerate to a particular velocity, let's say from rest, a car starts and then accelerates to 20 meters per second. After getting to that 20 meters per second, it can continue at that 20 meters per second motion for another, let's say this acceleration happened in, let's say, 5 seconds. After getting to a speed of 20 meters per second, it can continue at that speed for another 10 seconds, so that 5 plus 10, do you understand what I'm saying? So that 5 plus 10 will now give us 15 here. So if it continued at that 20 meters per second speed for another 10 seconds, that means the time will now be 15 here. Its graph would look like this. You understand? A train or a car starts at 0 meters per second, accelerated to 20 meters per second in 5 seconds. I can put, if you like, you can use your pencil to draw a broken line, showing corresponding time and velocity, that's showing that it attained a velocity of 20 meters per second after 5 seconds, starting from 0 meters per second. Now, if it continued at that velocity for another 10 seconds, 5 plus 10, this is 5 here, plus 10 will give you 15 here. So I'm going to mark 15. That means I'm going to mark what? 15 here. Is that clear? So this is how my graph will look like. In this kind of question, we might also be told that after another 10 seconds to make 15 seconds, the train decelerated to rest. The train or car decelerated to rest in 10 seconds or in another 5 seconds. So 15 plus 5, this place will be 20. Can you see the logic there? Decelerated to rest in another 5 seconds. So this place will be 20. Time in seconds. Let me label that axis. So this is a velocity time graph of that kind of motion. You understand? So you can use your pencil to indicate corresponding time and speed here with broken lines. Although that's not compulsory anyway. All that is not compulsory. But if you like to add it, to make your diagram clear, you can put it. So let me give you one last example. One last example before we go to. Let me give you one last type of velocity time graph before we go to the solved problems. You can be told that a car starts from rest, time in seconds, starts from rest, accelerated at a very high accelerated at a very high rate, you understand, for 3 seconds to get to a velocity of maybe 20 meters per second, and then reduced its acceleration, you understand, to get to another velocity of maybe 30 meters per second before maybe continuing at that motion, continuing at that speed for another. This could have happened for 3 seconds. This acceleration from rest to 20, could have been set to happen for 3 seconds. So that part will look like that. Now, it could have, gone from 20 meters per second to 30 meters per second. Acceleration again. In another words, in another 5 seconds. So this will be 8. 3 plus 5. 3 plus 5 will now give you 8. Are you getting the logic here? So, we could have been told that maybe after attaining 30 meters per second, it continued at that speed for another 5 seconds, which will make this 13 before decelerating to rest in another 7 seconds, which will make this 20. So invariably, this kind of motion we have 4 stages. Stage A here, it will have stage B here, it will have stage C, that's the stage of constant velocity, then it will have stage D, the stage of deceleration. So these are just the basics of velocity time graph and speed time graph. So in our next video, we'll use these graphs and the equations of motion we have learned to solve some basic problems or some simple questions on linear motion.